This meeting is being recorded.
Okay, so yeah, today we'll do a transmitter module implementation in the thing. Lastly, let me recap. Uh, we created a simple baud rate generator which takes a input clock, and based on our baud rate for transmitter receiver, we are generating a 16x from the reference clock. We are generating a 16x uh, clock, okay, which is like input clock will be divided by that much, like 16x, okay. So we saw many things, right there. We solve uh, how to get a divisor for that. So I have a table for like for standard baud rates, what is the divisor to get that. Okay, so today we'll continue on tx uh, block. Okay, so this is the block diagram, where we have like main, we have one pulse generator which is some kind of counter, because as I told, right, the input to our module will be some reference clock, but based on our baud rate we should limit our transmitter rate to match that baud rate. Okay, for that we may need to regenerate some more uh, clocks. So that is the purpose of this pulse generator. Okay, so input will be some baud signal, and after that, like again we will generate a 1 by 16th clock of that. Okay, so and there is a shift register module, so which will take the parallel input, okay, which we are about to transmit, and make it a serialize based on the UART protocol. Okay, so in addition to that, we should know how many bits to transfer, what are the whether we require parity or not. Many things will be depending on the control, right? So that those controls will come from the outside, and through the UART TX control. So this will control when to send the data, uh, and other things we will do through control. Okay, yeah. So the purpose of the shift register is just make the serial bits out transmitted. Okay, in this implementation, like we define a register which is every clock it has to shift to right and transmit on the TX pin. So initially it should be load by some parallel data. Okay, and we have to here every clock we should not shift, because that clock, I mean, when to transmit is like each bit should have a I mean period which should match with the baud cycle. That means, say if I say my baud rate is 9600, that means every second, I mean, per second, I should have a 9600 symbols. So in your transmission, like a symbol is nothing but a bit, so it should count to the 9600 bits per second. So if you calculate like what is the width of one transmitted bit, is like 1 by 9600, right? So it will be in the microseconds. But if our clock is at some say 100 megahertz, okay, every 10 nanoseconds you can send a bit. Okay, but that is not what we want. We want to wait for some bit period, send the bit, and wait for next bit period and send the next bit. So that's where this yeah, this pulse generator and all those things will come into picture. Okay, so yeah, this is the IO pins, uh, IO ports for our shift register. The whole transmitter logic is depends on this shift register. Okay, rest of the modules are just helper to generate a control and other things, but the whole logic for the transmitter will be in this shift register only. Okay, so we have a clock and reset, and there is a output which is 1 bit txt. is the actual transmitter which is going to the top block. Okay, and there is a input data. Okay, and these are the control signals, like there is a input data coming in, but when to take that will tell by load. Okay, and we are defining other handshake signals like done and busy. That means if the module is busy, this will be high. Okay, once this busy goes down, then only this load assertion will have a effect. And once that is done, during the transmission, this busy will is not ready to take the next load, right? So this will be high, completely high, till the transmission is over. And this done is a single cycle output. So once the transmission is done, it will just tell done, like. Okay, and there is a shift enable. Okay, just now we told, right, we cannot send on every clock. Okay, this clock can be anything, right? We don't know. It is a system clock. It can like in our case we are running at 100 megahertz, but every cycle we cannot transmit. Okay, so that's where this shift enable will come. So when shift enable is high, at that time only we will send the serial data out on the txt. Okay, then yeah, control logic I told, right? So maybe in this session we may not do a control logic, but just let us, because whole transmitter module logic will be here only. So we let us focus on this shift register implementation, and we'll go and implement this thing. Okay, first thing we want is this pulse generator, which we are going to implement now. Okay, yeah, for now, like I will skip the control, like I will first get this pulse generator and this shift register. So in this, and maybe let us integrate this stop in the UART module. Okay, okay, okay. Oh, so okay, this is the tx module which we are integrating in the top level. Okay, so we have a clock reset and txt, and data in, and board O coming from here. Okay, so what we required here is yeah, data in, maybe we can just define logical, yeah, data in actually, which is connected to our tx module. Yeah, but as of now, like just I'm declaring, I'm not connecting anywhere. Okay, I can just keep it, or I can do like wire. Okay, so we have instantiated here, and so with this thing, like a top level, we're done, and we can fill this thing. So like a pulse generator, what means like this is a counter to generate the pulse. Okay, based on our requirement. Next we will instantiate shift register. Okay, then control logic. Okay, so today we will focus mostly on these two things. Okay, so our aim is to take write a implement a module and test it, like we will load data in with whatever value we want, and make sure we have that busy done signals working properly. And once we load, our data should be transmitted on the txd port. Okay, but how will we test it? Like we will use cocotb UART extension, and we will verify with a receiver logic. So whatever we transmit, other side that model should receive the same data, so such that like we can verify. Okay, so yeah, let us go and implement this thing. Okay, so what kind of counter we required? Maybe I just have one template. So we are going to implement this thing. Okay, we'll take this board as the input. Okay, like we are counting how many times this board I is 1. Okay, based on this clock. Okay, so this board I is the output of our board generator. Okay, we right this board O from the board generator, which is dividing the system clock and generating pulse, which is 16x higher than the required baud rate. Okay, so that's why again to get the transmission enable, we are again dividing that signal by 16. Okay, because the input baud rate is 16x higher than the required baud rate. So that's why to get the actual baud rate pulse, we are again we have dividing it. Okay, so this is the reusable counter which we are going to implement now. So where we are counting the input count enable. Okay, which direction to think I am defining, like we are counting from higher to lower value. Okay, so that means like yeah, start value and some threshold value I am defining. Okay, so I want to generate a 16x lower, I mean lower pulse, right, in frequency. So that's why I'm counting from 0 to 16. So that means input this count enable, it will count 16, and once it expires, that means once it reaches the end value, it will simply gives one pulse with I mean one clock cycle with pulse. Okay, that's how I am generating a 1 by 16th of the baud I signal. Okay, so maybe we have to get that. Okay, okay, I will create a empty counter.sv. Okay, yeah, so I'll make it that thing. Okay, so this is the thing copied from the template and end module counter. Okay, okay, so we have to define a counter logic. Okay, for the local signals, which is like count register. So here the width is 8 because in our case we are going to count from 0 to 16. Okay, which like we required some 4, uh, but I am just taking a 8-bit counter. Okay, which is more than required. Then okay, here what is the thing, like we have to count uh, okay, count register, that is increment based on the direction, and as well generate count expire once it reaches the threshold value. Okay, so there will be a start value and there is a threshold value. Okay, so it's initially it starts at the start value, and based on the direction it will count. Okay, and once it reaches the threshold, it will go back, the counter will go back to the start value. At the same time, during that cycle, this count expired will be asserted. Okay, yeah, but we have to be careful while implementing this thing. Say sometimes you have a uh, different value, because these are coming as a ports, right? So say you started at higher value and keep on counting, like count up, and if you give a different threshold which is not in that range, like a counter range, you will never get a expired. So maybe as a good practice for the real things, we need to add assertions and other things, but for now let us assume we use this within the valid range. Okay, so let us yeah, do this thing. Oh, okay, these things anyway, okay, these things anyway we required. Apart from that, we may require some so this is simple counter where just based on the directions it is doing, but we want to use the start value and threshold, right? So okay, here we are just counting this count enable, like every cycle how many times this count enable is high. Okay, yeah, but we required some initial values, right? So we cannot directly go to the zero. So assume once it is reset, we'll start at some start value which is a input port. And similarly, like if the count if the count direction and once it reaches the threshold, right, what we want to do is we want to come back. Okay, we want to come back, say like this, once we reaches the threshold value. Okay, okay, just it may be another thing. Okay, in normal condition we keep on incrementing, but there is boundary conditions, right? Once we reach, okay, once we reach some conditions, we should uh, we should be um, okay, so that means we should go to else condition, this boundary conditions. Okay, these are the boundary conditions where we go back to the start value. Okay, so we will see what is that. Okay, just I'm taking this. Okay, as a good practice we always guard with I mean use begin end, begin end. So for every block we will use begin end only. Okay, so but what is the condition? uh, so if we are moving in the upward direction, that means start value to thing like okay, so this may be some different thing, right? To handle the boundary conditions carefully, we are adding this thing like once we are counting upward, and once we reach the threshold value, and we will again come back to the start value. Okay, uh, Okay, I think we have added this one. Okay, these braces we have added, I think. Okay, so in the TX UART, we added reset control and other things. This TX enable also we did. So let me define logic TX enable. Okay, which we connected to the count expire. Okay, we can directly we can see we have implemented this counter well and we instantiated here. Okay, so what I will do is I will go and add this new file. Okay, uh, yeah, we have not added this thing yet. I will just comment it. TX we have added. Verilog sources will add our counter.sv. Okay, so what we can do is like we can reuse the same test which we did for the UART baud rate generator. Okay, so we have a 100 megahertz clock and from there we are generating a baud signal which is 16x higher 16x higher than the actual baud rate, and again we are dividing that signal to actual baud rate. Okay, so we should see this signal, this RX enable signal, sorry, TX enable signal to actually match with the baud rate. Okay, uh, so let me do that, like make. Okay, so let me recap. Like so far we have designed a pulse generator to generate a pulse which is matching with the actual required baud rate. Okay, so yeah, something in the top level we had. What happened? Uh, we have added TX also, but yeah, let me see. Oh, okay, I'm not sure. Okay, yeah, simply like we removed one comment. Yeah, now it is. Okay, there is some data in location of personal. Okay, it says duplicate. Okay, I think we already declared the data in. Okay, we already declared here. So I'm making it wire because like I want to for this test I want to control this data in from the Coco TB. So if it is logic, I think somehow I'm unable to handle it. So yeah, but except that like you can declare it as a logic also. Let me check whether we have enabled waves or not. Okay, we have not enabled waves. Mhm. Yeah, with the latest version of Verilator, I am facing some issues with generating FST signals. Okay, let me see if that was resolved or not. But otherwise, if it is not working, I will move to VCD file. Okay, so I think we got. Let's see if we get. Mm, sim build. Are we getting any? Okay, so I think that was so. Instead of trace FST, I will just use the trace, so which will give the VCD file. Okay, no VCD file. Yeah, I have to compile the source code again with these things. Okay, this will come under compilation only. Okay, I will check the documentation and come back. Yeah, so this is not a compile arc. Uh, this is the extra. This is the new verilator requirement. Otherwise, previous thing also should work. Okay, so this was done. We're able to see the this. Okay, so we have this dump dot VCD. So we can use GTK wave uh, dump dot VCD. Okay, so I will focus on the board generator. sorry, in the TX counter, like we have a baud signal in, which is come from the baud generator output. Okay, this is okay. Then there is a TX enable, which is coming from our counter, which we have generated. Okay, this is not working as we required. Mm, okay, maybe let us go here and see what is the issue. Okay, there is a clock, there is a direction like upward direction, and reset is there. Start value, threshold value, we put F, and this is the counter register. And this is the counter expire and the count enable. Okay, so we gave start value of as a 0 and threshold value as F, and the count register, okay, starting with 0, that the count register is okay. So the direction we put 1, so that means incrementing. Okay, once it reaches the threshold value, actually it should give a count expired. Let us see and debug what is the issue. The count direction is 1 and count reaches the threshold value. Should come back to 0. Okay, wait. Okay, I think we are doing correctly except one. We didn't assign this count expire, right? We didn't do that. So yeah, we just missed. Let us assign that. So once it reaches the threshold value, okay, and there is a enable, then we just limit the count. I mean, this count enable, I want to limit to that period, so that's why I'm adding like okay, so I'm adding to the counter expect. Now if you run, you should see that signal also. Okay, so I think if you refresh, now you can see like based on the baud rate, this tx count expire will be done. Okay, so I think initially by default we configure for 9600 baud rate, right? So this entire signal, like we got only one pulse, that means one bit period. So I think it is roughly around 100 nanoseconds, sorry, 100 microseconds. Okay, but later I think in the test we are increasing the baud rate by configuring the baud. I think we can go back to the test and see what which we programmed. Okay, so what we did is, yeah, I think we updated 54. Okay, we write 54. So that means like every 54 cycles we are counting. So which I don't know what is that value, but let us see from the table. So I'm opening the last weeks. So 54 is like this one, like okay, 1152. Okay, so this is the baud rate we configured after that. So that's why we are seeing that very frequently coming. So that means here, if the baud rate is that, I think roughly every, okay, from here to here, what is that? Um, it is showing like uh, it is like in nanoseconds only. Okay, so like this is, okay, cursor is at 2500, 2800. So roughly 300 nanoseconds is the uh, uh, difference between the each pulse. So this is very fast compared to the earlier one where we like we got in microseconds, hundreds of microseconds, one bit. So here every pulse will tell like to transmit the next bit. Okay, so we are done with the counter logic. So I'm closing this thing. Let us move to uh, the shift register. Okay, so I will remove the older one. Okay, I can remove from here. Shift register. So I will create okay, I will create a new shift register. Okay, so okay, so from the PPT I am copying, or I will use that UART sync to read the data and check whether I get what I transmitted. Okay, so this is the way I have to do. Like I am using UART sync read. Okay, this will do based on our initial configuration. It will do read the incoming stream of bits and may prepare a frame and use back as a uh, bytes, okay, data. Okay, then I can say assert this data is equivalent in bits, okay, in binary, like hex format, because this will gives back bytes, okay, byte array. Okay, so what we have sent in X is 41. Okay, so I have to just make sure once the transmission is done, like I am just reading using the model and make sure the received data is same as what I transmitted, like 41. Okay, and yeah, I can tell I can format a string. Expected is 4 1, but if it fails, okay, to get I can say use this thing. Okay. So we are expecting 4 1, but if we get a different value, this should print that. Okay, so I think it will take some time to transmit all bits. Okay, so it's done. Like you can see, right? Since it says pass, what I expect is this was passing, and even this was passing. Okay, so you can see that from here. Okay, say see this read byte we got as a 0x41, which we actually transmitted, right? So I think with this, our transmitter module is working correctly. Okay. Only thing like we have a fix